This reaction is also combustion, but it's clearly indicating that it's incomplete, which means you can form carbon monoxide, and if there's definitely not enough oxygen present for every time it combusts, then you might also just get pure carbon, and so there's a bit of mixture. So this one's telling you that it only wants carbon monoxide and water. There's different ways you can do this and show incomplete combustion. Kind of depends on what you're trying to do in your answers. But this reaction you'd have, sorry, I haven't done the color change, light blue. Got the H10 gas. Again, I've got the advantage knowing the first four gases. Oxygen, and so all I do is write carbon monoxide instead of carbon dioxide, and do the same thing, 4, 5, and that gives me 4, 9, and so I need like to put 4.5 here, and 9 over 2 is 4.5, so 4.5 times 2 is 9 oxygens. I'm happy to leave that. In my early days, I would say you can't have half an oxygen. And so I would go and put a 2 everywhere, like go 2, 9, turn that into 8 and 10. I'm now happy with this, okay? The reason why I'm happy with this is it often in your year 12, you look at how much energy you would take to burn 1 mole of fuel, so it's always good to that. And if you're trying to show ratios, so it's all about in combustion, the ratios. If I use propane and pentane as an example, propane only requires 5 oxygens to 1 fuel, and that's more likely to happen. So if you're burning propane, you're more likely to get complete combustion than if you're burning pentane. So for pentane to burn completely, you'd have to have 8 to 1. So that ratio is different. So you got 1 to 5, 1 to 8, and this is 1 to 4.5. So if you only had 4.5 oxygens present, you'll get incomplete combustion. And you can do the equation if you want to see, it'll be somewhere in between 5 and 8 to get complete combustion. In real life, you'll get a mixture of complete, incomplete, and very incomplete when you just get carbon soot. Carbon solid soot. That's the black residue. After blue, yellow, and then we'll go orange, pink, yellow, then pink. Lead carbonate reacts with phosphoric acid. This is acid. This is acid plus metal carbonate. So we go lead. Don't know why it's lead 4, not very common. We've dealt with this before. We're going to call that a solid. Phosphoric acid. Or aqueous. Is this actually a double up? What did I do lead 4? I feel like it was early on. It's not a double up, it's very similar. Alright, then we're going to get lead 4 phosphate. It's going to look weird. Lead. I'm going to drop the 3 of the phosphate, and I need 4 lots of phosphate in solid form. And this is that's my salt, this is my water, and this is my carbon dioxide. Right. So 3 leads, and look at my leads. I'm going to put a 3 there. That's going to throw my carbons out to 6. I'm going to try putting a 6 there. My hydrogens here are 2 and 3. So I'm going to put a 2 there and a 3 there to get them to 6, and then I'm going to evaluate where I'm at. Phosphates look out. 4 there. Maybe I should have started with phosphate. I go 4 on the phosphate, so the phosphates are balanced. What's that do to my hydrogens? I got 12 there, so I need 6 there. Okay, a lot going on. 3 leads, 3 leads, 6 carbons, 6 carbons, 6 oxygens. 6 oxygens. I feel like 6. No, there's 18 oxygens, and I've got 18 oxygens. This looks right. Hydrogens are 12 and 12. Phosphates are good. Wow, that was tricky. Right, solid silver phosphate dissolving into ions. Okay, this is just called a dissolution or dissolving. It's actually really good to know. So you got silver phosphate. Silver is 1 plus. So I need 3 of them to match the phosphate, and it's going to dissolve slightly into its ions. So actually, I should write. It's going to split into its 3 ions, aqueous, plus its 1 phosphate ion, aqueous. And they're no longer attached. They're actually dissolved. Right, and that's all it was asking for. To purple, we go orange, then green. Okay, magnesium hydroxide is Mg. Need 2 hydroxides. It's a solid. We got, sorry, I was doing the dissolving of it. It's actually reacting it with sulfuric acid. This is acid. Oh, this is our first neutralization reaction, I believe. Acid plus base goes to salt plus water. My salt is ionic compound, magnesium sulfate plus H2O. And I gotta balance it. It looks like I put a 2 there. Does that solve it? 1 magnesium. How many waters? I got 4 hydrogens, 4 hydrogens. Yeah, that looks good. Alright, we'll move on. Orange, we go green, then purple. Okay, acetic acid is up on your. It's an acid, it's always aqueous, and it's on your polyatomic ion list. Lithium hydroxide is just a base. Haven't really explained. If you want to, might explain what a base is. That's anything that brings down the ratio of water. It's actually in the top right of this document that I skipped over. And so you're going to get lithium acetate, like that, aqueous, and water. Literally, I will draw the water. All that happened is that hydrogen went to that OH minus and made H2O. So an acid is anything that brings up hydrogen ratios. This is anything that brings down. Bases are anything that brings down that. And neutral water is when the ratio is 2 to 1. It's probably the most simplistic way to put it, but it's a huge focus of Year 12. It's a whole module. Purple, I believe. Lead nitrate and potassium iodide. Okay, this is actually, it looks like the last 2 are precipitation reactions, and this is why I've put this data sheet. So this data sheet is used in Year 11 and 12, and although you don't need to use it until you're in Year 12, because KSP, which the degree of solubility, these are a list of all of these precipitates, and all these numbers do is indicate the degree at which they're insoluble. So the lower they are, the more insoluble. So I think lead phosphate is the most insoluble, 10 to the negative 43. Anyway, we go over here, we got lead nitrate. It's going to be aqueous. All nitrates are aqueous. And potassium iodide. This is actually a famous experiment because it produces this compound, lead iodide, which is a yellow solid, very pretty solid. And it should be down here, lead iodide, 9.8 times 10 to the negative 9. It's fairly insoluble. And what do we got left? Potassium nitrate. 2 reasons why that's soluble. To be really particular, they're not actually reacting, they're just there. So it's actually just K plus floating around in nitrate and minus there, but all that kind of stuff gets done a bit later. Last color is light blue, it runs favorite. Ammonium chloride plus silver acetate. Ammonium's always aqueous, so I skipped over that. Aqueous. Acetates, I wrote acetate, sorry, I shouldn't have put the extra H on it. Right, and this is also a precipitation reaction. I'm going to make silver chloride. Okay, silver chloride, you can confirm when you have this list. Silver chloride.